Next chapter, second chapter, vector space 1. So, definition of vector space and examples. Definition of vector space: V is an arbitrary non-empty set. Vector space is also called linear space. Vector space or linear space. And the definition is what? Let V be any set, arbitrary non-empty set of objects, that is elements, on which two operations are defined, denoted by addition plus and multiplication, denoted by addition and multiplication, defined as a addition and multiplication by scalars called sum and scalar multiplication. So there are two operations on the set V. One is addition and one is multiplication, and addition is called sum and multiplication is called scalar multiplication respectively. And if this set elements of V, that is suppose U, V, W is in V, and KB and K and L are scalars. Scalars means real numbers. K and L are scalars means real number. Then V is called vector space or linear space over R, or just say a real vector space. It's called real vector space or vector space over R or linear space over R if the following axioms are satisfied. So V is any non-empty set, and the two operations called sum and scalar multiplication, these are not usual addition or usual multiplication. The definition of addition and multiplication is given in the example. And if the elements of V, suppose U, V, W are the elements of V, suppose the elements of V and all scalars K, L, M, N, all these scalars satisfies the following 10 axioms, then V with these two operations is called a vector space. So what are that 10 of axioms? The first two one are called closure axioms, the next four are called addition axioms, and the next four are called scalar multiplication axioms. And if V means the elements of V satisfies these 10 properties, then V is called a vector space. So first property is called closure axiom. Suppose it is denoted by C1. This is not standard notation. C1, C2, A1, A2, A3, A4. These are not standard notations. For convenience, we use these notations to denote these properties. Otherwise, we can denote these properties by numbering 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Okay. So first two are the closure axioms. For U and V in V, U plus V belongs to V. That is, U plus V belongs to V for all U and V in V belongs to V. That is, addition of every two elements of V belongs to V. Addition of every two elements of V belongs to V is called closure axiom. Close for addition is called close for addition. Addition of every two elements of V again is the element of V. So next operation is what? For any scalar K, that is K is the element of R, and for any object U in V, that is for any element U of V, Ku belongs to V. Ku, K and U, their multiplication belongs to V. Okay, so this is called V is close for scalar multiplication. V is close for addition, the first property. V is close for scalar multiplication. That is, any scalar and any element of V, their multiplication belongs to V. Okay. If we take the multiplication and addition as a regular, your usual addition and usual multiplication as a meaning of this sum and scalar multiplication, and if we take the set of natural numbers, then set of natural numbers is close for addition. The first property is true for set of natural number, because addition of every two natural number is again natural number. But this is not true. The second property fails for natural number. That is, if you take as K as scalar, scalar means element of R. Scalar means element of R, element real number, any real number. Suppose K as 1/2, and if we take element 3 of natural number 3, of natural number, set natural number, then 1 half into 3 is 3 by 2, and 3 by 2 does not belongs to natural number n, set of natural number. 3 by 2 is not natural number, and therefore the second property fails for natural number, and therefore capital N, that is the set of natural number, is not vector space. Second property fails for the set of natural numbers, because any scalar and any element of natural number n, their multiplication does not belongs to n. We have some scalar, that is suppose k is 1 half, and suppose u is 3, then ku is 3 by 2, and 3 by 2 is not natural number. So set of natural number, set of integer also, set of integer z is also not vector space or linear space, because second property also dissatisfy in the set of integer. Then next property is addition. A1 is denoted by A1. U plus V is equal to V plus U, is called commutative of sum, or commutative law, commutativity of sum. That is U plus V and V plus U both are same. Then U plus V plus W is equal to U plus V plus W, is called associativity of sum. U plus V plus W and U plus V plus W, this addition, this LHS and RHS both are same. For all, obviously for all U, V, W belongs to V. Then third property of addition, there is an object 0 in V, there is an element 0 in V, is called 0 vector for V, such that U plus 0 is equal to U for all U in V. There exists one element is called 0 element. The notation for 0 element is 0, such that U plus V, U plus 0 is U for all U in V. That is, if you add that element in any element of V, then we have the same element. U plus 0 is equal to U for all U in V. If such a element exists, must exist in V. A3, property A3. Then property A4, for U in V, there is an object, there is an element minus U in V, called negative of U, such that U plus minus U is equal to 0. So additive inverse, U minus U is what? Additive inverse of U. So U and minus U, that is negative of the number, exist in the set. For every element, its negative also exists in the set, because their addition, such that their addition is 0. So if you take set of natural number, then this property is also dissatisfied, because in the set of natural number, the elements are 1, 2, 3, 4, 5 up to infinity. If you take 3 element, then its negative is minus 3, but minus 3 is not the element of n set of natural number. So this property is dissatisfied for natural number. This A4 property is satisfied for the set of integer, because set of integer is what? 0, plus minus 1, plus minus 2, plus minus 3. These are the element of Z. So in Z, this property is satisfied. A4 property is satisfied for Z, because if we take 3, then its negative minus 3 is also the element of Z. And the A3 property is also dissatisfied for set of natural number, because 0 is not natural number. 0 does not exist in n. But this A3 property is satisfied for the set of integer. Okay, A3 and A4 satisfied for the integer, but this property C1, C2 is not satisfied for integer, and therefore set of integer, that is Z, is not a vector space or linear space over R. This property, if you consider this property U plus V and V plus U, this is satisfied for set of natural number as well as set of integers. This property is also satisfied for set of integers, set of natural number, but this property, these two properties are satisfied for set of integers, but these two properties are not satisfied for set of natural numbers. Then next property, the 4 properties are called scalar multiplication axioms or properties, and then M1 is what? Ku plus V is equal to Ku plus Kv for all U and V and for all K, and K plus Lu is equal to Ku plus Lu for all K and L belongs to R, and for all U belongs to V. KLU is equal to KLU, and 1 into U is equal to U. So these are the four properties of scalar multiplication axioms, and if all these 10 axioms are satisfied by V, are satisfied by V means what? Elements of V. Then V is called vector space. Just we say V is called vector space, or V, right, in round bracket V, comma plus comma dot is called vector space. Okay. So the objects of V are called vectors. The elements, if V is a vector space, then the elements of V are called vectors. Uh, and hence we denote elements of the V as just u v, or we can denote it is by u bar v bar. Direct write u bar or u raised to u raised this arrow, v this arrow. Yeah. Read it as u bar v bar. Okay. So the usual definition of vector is what? The quantity having direction and magnitude. This is not the definition for this vector. Just the elements of vector space are called vectors. Okay, that is the quantity has directions and magnitudes. It is not the definition of vector in this chapter. Vector means just the element of V. They may be scalar. Okay, so if these 10 properties are satisfied by V, then V is called a vector space. So some examples of vector space. Obviously, we discussed that set of natural numbers and a set of integer are not, these two are not vector spaces. So set of real numbers, suppose capital R, the set of real numbers is a vector space with addition of two members in R, usual addition of two real numbers and usual multiplication. That is, we know that 2 plus 3 is 5 and 2 into 3 is what? 6. This is the usual addition, usual multiplication in R. So with respect to these two operations, usual addition and usual multiplication, this R set of real numbers becomes a vector space. That is, the set of real numbers, the elements of this set R, and with respect to the addition and multiplication, satisfies all these 10 properties. That is, if we check these 10 properties for set of real numbers, then what do we have? If we take any two element from R, then U plus V belongs to R. Addition of every two real number is a real number. Then if we take any scalar means real number, and if we take any element of capital R, that is in this problem V is R. Then Ku is also the element of R, because any multiplication of two scalar is two element of R, two real number is real number. Also, this property is satisfied for all elements of R. This property is satisfied for all elements of R. 0 exists in R, 0 vector. 0 is real number. Then for every element in R, its negative also exists in R. And these properties are also satisfied because we know that multiplication is distributive over addition. Ku plus V is what? Ku plus Kv. Multiplication is distributive over addition from left side and right side. Okay, left distributive law, this is right distributive law. Both are true form. This is the associated property for multiplication. We know that the multiplication of three real number is associative. That is, if we have to multiply 2 into 3 into 4, then we multiply 2 into 3 first and then multiply by 4. We have the answer 2 into 3 is 6 and into 4 24. And if we write the calculation like this, 2 and first multiply 3 into 4. So 3 into 4 is 12 and 12 into 2 is what? 24. So we have these two sides are same. So this property is also satisfied for real number. Obviously 1 into U is U for real number. For all U belongs to R. And therefore set of real number R with the two operations that are what? Usual addition and usual multiplication. So R is a vector space under these two operations, set of real number. Okay, but the set of natural number, the set of integer are not vector spaces. And next example, V is equal to R square. R square means what? R cross R. be a set of all order pairs of real numbers. Obviously, we know R square is what? Is the set of order pairs such that xy belongs to R. This is R square, set of order pairs. Similarly, R cube is what? XYZ, set of three tuple. R raised to 4 is set of four tuples. That is XYZW, such that XYZW belongs to R. So this is R square. And we define the two operations. Suppose u bar as the element xy and v bar as the element x dash y dash in R square, means the element of R square. Then the two elements are equal, obviously, if x is equal to x dash and y is equal to y dash. U bar plus v bar is the addition of these two. Xy plus x dash y dash is x plus x dash comma y plus y dash. I can order pair the corresponding addition of the corresponding elements, corresponding coordinates. Okay, so x coordinate, y coordinate, addition of y coordinate. Okay, and the scalar multiplication for scalar k means for k is a real number actually. Scalar means then k into u bar is k. U bar is this xy, so is kx ky. So with respect to these two operations, sum and scalar multiplication, this R square is a vector space. That is R square, the elements of R square, and with respect to these two operations, sum and scalar multiplication, satisfies these 10 properties. That's why this R square set of order pairs, all real order pairs, is a vector space or is a linear space. So we have to uh, prove these 10 axioms. So first axiom is closure axiom. So we have to prove that addition of every two elements of R square belongs to R square. Suppose u and v are any two elements, and then what is u plus v? U plus v is this x dash plus x plus x dash comma y plus y dash, and this is again order pair. This is the element of R square, because x and y, x and x, y, x dash, y dash, all are real number. Addition of two real number is real number. So this is real number, this is real number. And therefore u plus v belongs to R square for all u and v belongs to R square. Also k into u is this k, x, y is kx, ky is again order pair. This is the element of R square. And therefore ku belongs to R square for all u belongs to R square and for any scalar k. And therefore the first two axioms are satisfied for R square. Then next axiom is A1. Suppose u bar is xy, v bar is x dash y dash, w bar is x double dash y double dash, be vectors in R square, be any vectors in R square. Then we have to prove the properties A1, A2, A3, A4. So u bar, we have to prove first u bar plus v bar, u bar plus v bar is equal to v bar plus u bar. So what is u bar plus v bar? Xy plus x dash y dash is x plus x dash order pair, x plus x dash comma y plus y dash, addition of these two. And obviously we can write x plus x dash as x dash plus x, because sum in R is commutative. Addition of real number is commutative. 2 plus 3 and 3 plus 2 both are same. Then write y plus y dash as y dash plus y. And then we again use the definition we have. It is addition of x dash y dash plus xy. Addition of these two is this. And then it is u bar, v bar plus u bar. So we have u bar plus v bar is equal to v bar plus u bar for all u and v in R. Then A2 property, we have to prove this u plus v plus w is equal to u plus v plus w. So consider u plus v plus w, u plus v plus w. Then what is u? U is xy, v bar is x dash y dash plus w bar is x double dash y double dash. Then addition of these two is what? X plus x dash. Addition of these two is what? Y plus y dash plus x dash, x double dash, y double dash. This is by using the definition given in the example. This is the definition of sum. Then the sum of these two, again by using the same definition, the sum of these two is x plus x dash plus x double dash and y plus y dash in bracket plus y double dash. Addition of these two, again by the definition of sum given in the example. So this is the addition of real number And the addition of real number is associative, associativity of sum in R. So x plus x dash plus x double dash, we can write x plus x dash